Welcome everyone to another Guideline Geo webinar. Thank you very much for joining us. We're going to be looking at how we can do resistivity surveys in and on water today, specifically using the Terameter LS2. I had a quick look at the list of participants. There were a few names I didn't recognize, so I'll do a quick introduction to both myself and the company. For those who are familiar with both myself and the company, I apologize. You'll have seen this an awful lot. My name's Jimmy Adcock. I am the product manager for the ABEM range at Guideline Geo. Geophysicist by training. I worked as a surveyor for many years and then joined Guideline in 2015. I took over the product manager role at some point during COVID, and like everyone else, my timelines have become a little bit blurred, but I think it was late summer 2020. Guideline Geo, we are a manufacturer of geophysical instruments. We manufacture GPR, seismic, resistivity, and transient electromagnetic systems. We can trace our roots back to 1923, which is when ABEM actually was founded. And all of our products are made in Sweden, which is where the heart of the company is. So head office is in Stockholm. We have research and development a bit further north in the city of Umeå. And then the town of Malå is where our factory is. So that's up near the Arctic Circle. I'm based in Manchester in the middle of this map. So I kind of sit in the middle of all the time zones quite nicely. Okay, that's enough of the boring stuff. Let's get on with what we're here for. And that's talking about how we can do resistivity in marine environments. So I thought it would be a good idea just to start with about 3 slides just on theory, so we can kind of understand what the major complications might be if we try and apply specifically ERT in a marine environment. So if we're doing survey on land, everything is very simple. We have our multi-electrode cable laid out, and the instrument is going to switch between different arrangements of electrodes to gradually build up a pseudo section, i.e. a data set of apparent resistivity values against position along the line and depth. Now, the thing about surveying on land is that the situation that we find ourselves in is fairly simple, because the current can only actually go one direction. It can only go downwards. So we refer to that as the half space, because the current is flowing into the ground beneath us, but it's not flowing into the air above the array. So we have a half space for the current to flow through. Obviously, if we then change the scenario and actually put our electrodes into water, well, that half space assumption is no longer true. We now have electrodes that are sitting between the sort of geological material beneath and the water above. And so obviously the current can now flow in more than one direction. It can flow in the whole of the space, not just the half space. So that has big implications on how we come to process the data afterwards. And we'll talk about that later. I get asked a reasonable amount about sort of marine resistivity, and so that's why we thought it would be a good topic for a webinar. And I thought I'd have a quick look and see if anyone's done anything recently that I could sort of highlight. So I went onto LinkedIn yesterday afternoon. I typed in ABEM, and then I put in a bunch of terms like water, river, sea, lake. And in the last month, actually, we've got 2 users who have published a post about doing marine resistivity. And really helpfully, they are both in sort of the different ends of the way that you would approach a survey. So on the left, we have Emil at Dam Geotechnical Services, and he's doing the survey from a boat in a shallow sea environment, so salt water, and the cables have been sunk to the bottom so that they sit on the seabed. Then on the right-hand side, we have Reinhard from CDM Smith in Germany, and he's kind of doing the opposite. So he's not on a boat, he's sat on the side of a river, and the cables are therefore in fresh water, and they're not actually sunk to the bottom, they are pinned across the top of the river. So this is sort of 2 of the different approaches that we can take, and we'll discuss both of them in the next coming few slides. So what are the considerations that we need to make before we start our survey so we can decide on the best setup? Well, the first thing we want to know is, do we have the right hardware already, or do we need to invest in something else? So the instrument itself is perfectly suited to doing marine resistivity as it comes out of the box. But the thing that we might need to change is the way that we have our cabling set up and the type of cables that we use. So there are really three options for the type of cabling that we could undertake the measurements with. First are just our standard cables, our regular spread cables with a wire wound takeout, stainless steel takeouts. So these are the regular cables you'd use on land, no different. The downside of using these is that they are not really designed to be fully submerged for long periods of time. Obviously, they're waterproof because we throw them down on the ground and we work in all kind of conditions, but actually sinking them into water is something different because obviously the pressure there is quite a lot higher than it would be at the surface. So standard cables are fine for sort of occasional dropping into water to take a measurement. Ideal example would be crossing a shallow river where the cable is either going to be just at the surface, pinned on either bank, or it's going to be, within a meter of the surface of the water. So not too shallow, so the pressures aren't too high, and we're only immersing it for a short period. Now, I'm talking about the main part of the cable here with the takeouts that we would normally clip the electrodes to. Obviously, the connectors on the ends, or the cable joints, if you've got a multi-section cable, they're not going to be designed to be submerged. They're waterproof, but not submergible. So we're talking about the main part of the cable. Part of the issue with the regular cables is not just water ingress getting into the actual body of the cable itself, but it's the fact that they have the wire wound takeouts. So they're made like that so that they can be more flexible. But the problem is that if you drop it into water that has a lot of sediment into it and it's under quite a lot of pressure because of the head of water above it, the sediment can get forced into the winds of that takeout, and then becomes very difficult to clean, and then that could potentially start to build up a corrosion layer. So we use these for, as I say, shallow short-term measurement. The next option then would be to move up to what we call dual purpose cables. So the big difference on these is that they have a solid stainless steel takeout. So rather than a wire wound one, it's a solid sleeve of stainless steel. So they're not as flexible, but they are much easier to keep clean and to clean when we remove them from wherever we've been undertaking the survey. They've got a slightly different housing around the takeout, which again just improves the protection against water ingress when there's higher pressures involved. So we can use these for regular survey on land because they're not very heavy. It's really just the takeout that's different. The main cable is the same. We can immerse these for much longer, and we can go much deeper, so about 30 or 40 meters depth before we would need to think about changing the type of cable again. And if we did have to change the type of cable again, well, then we would move on to what we call like full marine cables. And these have a larger takeout again, even better protection around those takeouts, and they're impregnated with a water blocking compound along the entirety of the cable. So it's a different cable that we're using to start with, and they have much better water protection. The full marine cables will also have a strain member within them. So this is a wire that sits in the middle to give extra strength to that cabling. So if we're using it, if we're towing it behind a boat, then we can not have to worry as much about the possibility of the cable snapping. So this would be for constant use in water. It would be places where we're going to be immersing it for a long time, especially areas where we might have a rough sea or riverbed where we might be worried about, as we move the cable, it catching on rocks or other debris and snagging. And we can use this in much deeper water. So up to sort of 100, 200 meters of water, these cables would be fine. They are, however, very heavy. The cable is much heavier gauge. It's got the strain member in the middle and the takeouts are larger. So they're not really practical for use on land like the dual purpose cables are. You would have to have a sort of mechanical deployment system like a cable reel on the back of a quad bike or a pickup truck, really to be able to move these easily around your site if you've got particularly long cables. So we've been talking there about the takeouts a lot, and we've been talking about stainless steel takeouts. So that's the most common configuration that you'll find. They're very, very strong. It's very easy to seal them or seal around them, even if you're going to be dropping the cable into very deep water. The only downside is that they can be prone to some surface tarnishing. So over time, you get a kind of electrolysis effect on the surface of the stainless steel, even though it is stainless, and that needs to be cleaned. So there's an example here where someone's been doing survey in seawater, and over time this film has built up on the surface of the electrode takeout. But a good scrub with a brush, excellent job for an intern or the youngest member of staff, and that will come up clean again. So it's just a case of being on top of the maintenance for them. The alternative would be to use a graphite takeout, which these are available on some cables. The graphite is much more resistant to corrosion, much more robust in that term. It doesn't require the same kind of level of cleaning. The downside of the graphite is that it's brittle, so it can get damaged. And obviously, if you're dragging a cable from one survey location to another, there's a possibility that they could break or get chunks chipped off them. So there's sort of pluses and minuses to the two different materials. What I didn't mention was that obviously when we're on land, we're using steel electrodes that we hammer into the ground and then connect up to the cable. For a marine survey in the sea, river or a lake, we don't use an electrode. We just allow the current to flow straight out the takeouts and into the water column or into the material beneath the cable. Now, these kind of considerations that we've made about the cabling and the takeout material, they are actually completely relevant to borehole surveys as well. So if we're doing borehole ERT, we'll be dropping cables into water-filled boreholes and then running our measurements like that with the current flowing out into the water in the borehole and then into the surrounding geology. And it's exactly the same considerations that we would make when deciding what kind of cables we would use for that. So that's hardware. Let's now talk a little bit about the layout, how we would actually deploy that cable once we've decided what we want to, or how we want to use it. So we have two options here. We can float the cables at the surface using fishing floats. That's probably the easiest way. So you get these big circular floats that go around the industrial fishing nets. You use those, you just push the cable through the middle, use enough of them, and the thing will just float just at the surface. And this is an excellent way to collect data because it makes the processing very simple. Because what have we done by putting them at the surface? Well, we've maintained our half space theory. The current isn't going to be going upwards, it's only going to be going downwards. The water column will act as another layer. So when we come to do our inversion, we would run it just as we would on land. We could improve the inversion by telling it something about the water column, for example, how deep it is, maybe even what the resistivity of it is. But if we didn't have that information, we could just run a regular inversion and it will treat that as one more layer. The downside of setting your survey up like this is that you really do reduce the effective penetration of the current. And we're talking about how we can analyze that later. But a lot of energy is lost into the water column by floating the cable at the surface. So it's only really practical if you are working over a shallow body of water. So a perfect example would be like a river crossing, where perhaps you're trying to analyze the geology ahead of planning, say, bridge foundations. There you might have 1 or 2 meters of water and then the geology that you're interested in. If you're only interested in the very shallowest geology or just the sediments and where they contact with the bedrock, then again, maybe it doesn't matter that you're losing a bit of energy into the water column because you're only interested in the upper couple of meters. So the obvious alternative then is to submerge the cable, drop it down onto the river, lake or seabed, and actually take the measurements from there. This is more complex when we come to do the inversion, because now we have lost our half space. Now we have this situation where the electrodes are between two layers and the current is flowing now in all directions. So for us to be able to run the inversion, we need to know two things. We need to know the resistivity of the water column, and we need to know how deep the water is, so that the inversion software can know how far up the current would be extending before it reaches the water-air interface. The positives are that we get much better penetration because we're not losing as much into the water column. The electrodes are sat on that sediment at the bed, and so therefore we get more current transferred directly into the stuff that we're interested in, into the subsurface geology. When we're designing a system where we want to submerge it, we do have to make a few more considerations about the design of that cable, though, because obviously we need to make sure that we get the correct lead-in on the cable. And so a lead-in is the distance from the connector on the end that attaches to the instrument, the distance from there all the way to the first takeout. Now, you can't have a connector, or you prefer not to have a connector that is within the water column. So you would define the lead-in at such a length that it allows you to get through the entire water column and have some spare cable to get to wherever the instrument is in the boat or on the banks of the water body that you're investigating. And especially if you're on a boat, just allows you a bit of movement without dragging the spread cable around on the bottom. A few things that are common to any kind of marine spread is that typically we work with just a single cable. So when we're on land, we would normally have a minimum of two cables, one each side of the instrument, but sometimes we'll split that into even more sections. But it tends to be less practical when we're trying to do a marine survey. It's much easier just to have a single cable that we can drag into position and then take our measurement from. So typically all of our takeouts will be on a single length of cable, and then at the end it will split into however many connectors we need for attaching to the instrument. So if it was a 64 takeout cable, then it would split to two connectors to attach to the LS. Let's say it was 128 electrode spread, then you would split to four connectors, two for the LS and two for our ES1064, the expansion box that allows you to add additional electrodes. The deployment of a single cable is obviously much easier in a marine environment because you've only got one section to deal with. When you get onto land, it's the opposite way around. Having just a single cable is not ideal. So if you've got these dual purpose cables, it might be that for waterborne survey, it's much, much easier to have a single length. But once you get on land, if you want to do a roll along, you normally don't take an entire length of cable and roll along the entire distance of that cable. You would normally split it into sections so that you get an overlap as you roll along. And the only way that you can do an overlap if you have a single length of cable is to disconnect all of the electrodes when you're working on land, pull the whole thing forwards, maybe half the cable length, and then attach everything back up again. So you need to balance your kind of cable design with how you're going to use that cable the most, and whether you're happy to compromise in either the dry environment or the wet environment. Those are all the kind of practical considerations that we would make for our surveying. I should actually say that for the most part, we're always going to be using just the same spreads and protocols that we do on the land, because actually in terms of data collection, there isn't a huge difference in what we need to do as the sort of raw steps of collecting those voltages that we can then calculate a resistance and convert to an apparent resistivity. So we can still use our Veners, our Schlumbergers, our gradient arrays. A lot of people, when doing marine survey, will use something like a Schlumberger, because even though it's slower, because it's a single channel protocol, you can only take one measurement at a time, it has a very good signal to noise ratio. And given that you're working with usually smaller signals because you've got basically a lower resistance in the material that you're pushing the current through, and you're losing signal into the water column. Anything you can do to improve signal to noise ratio is a good thing. So quite often people will use a Schlumberger rather than one of the multi-channel arrays, which would have been much quicker. So yeah, let's now move away from the kind of practical side of collecting data and talk about what we need to think about when we come to process that data. So actually the workflow for the first couple of steps is very, very similar to any other resistivity data set we might have, whether it's collected on land or in the water. So first step will be our QA, our quality assurance, checking that the data we're going to take forward for the inversion is good, and that we don't have any bad data points that would cause the inversion software to struggle to make a reliable model. So the normal steps we would follow would be to remove anything with a low signal quality, i.e. anything that has a high standard deviation associated with it, i.e. the signal was unstable during the measurement phase. Then we would take out anything that had abnormally low voltage measurement, so a low signal strength, so anything that would be sort of within the noise floor and so therefore would be likely to be less reliable. And then we remove finally any obvious statistical outliers, so any really, really high apparent resistivities or any very, very low apparent resistivities that sit outside of the main spread of values. Once we've done that, then we can export the data into whatever format we need for our inversion software. And we need to make a consideration at that point as well. So not all inversion packages will allow you to do marine inversion if the electrodes have been submerged. If you've got floating electrodes, then any software package can do it because, as I say, that will just be treated as another layer, assuming that you're not going to give any additional information to the inversion software before it starts. But if you've sunk the cable down, you need to have a package that can deal with the fact that you're not working in a half space anymore. So Res2D, Res3D, perfect example. That's a package that can deal with that and allows you to enter the additional information, such as the resistivity of the water column and the depth of the water column. So we export into the format that we need. We add in the additional information as required by the inversion software, and then we can do a final check of the raw data in that inversion package. So most of the software packages will have some way of looking at the quality of the data. You can make sure that your initial first pass has indeed got rid of all the bad data. So then we run the inversion itself, selecting parameters as we would if it was just a normal land-based survey, making decisions about whether we want to use a robust inversion where we allow the resistivity to change more rapidly within the model, or whether we're going to use smoothing to actually compress to limit the rate at which the resistivity changes. All of those normal considerations would still be made for marine data. Once we've got the result back out, exactly the same again, we would look at the model and we'd assess its reliability. So we'd look at it and say, is this a realistic model, knowing what we do about the geology that we've been working over? Are there any artifacts in there, obvious artifacts that we can say, well, that's definitely a problem with the inversion. Let's go back and try and correct that. And then the final step, which is extra important when you're working in a marine environment, is to assess the penetration depth. How well have we been able to get current into the subsurface? Obviously, this should be a consideration you make in any survey that you do, whether it's in land or in water. But in water, we know that we're losing energy into the water column. So we really want to double check that we're seeing deep enough in our real data, in our final model. And we'll look at that towards the end of this webinar. So I said Res2D was a great package for doing the marine inversion in. So I'm going to use that as the basis for the example of how we add additional data about the marine survey into the files. So when we export from LS Toolbox, our companion software that comes with the LS resistivity meter, it'll come out in what we call the general array format, which is one of the formats that Res2D can accept. And so that will have on it, at the very top of the file, some header information. So like file name, electrode spacing, the type of array that's being used. So this is general array format file with gradient array data. So that number just changes depending on whether you've done a Venner or a Schlumberger, whatever. Tells the software whether the values that we've exported are apparent resistivity or the kind of raw resistance values, how many data points are in there, and then whether or not there's IP data as well as the resistivity. So that's pretty much the same, again, whether it's a land-based survey or a marine survey. And then beneath that, it lists all of the data. So we have information on how many electrodes are in use. So there's 4. And then the coordinates of each of the electrodes are given in pairs. So A, B, M, and N, X and Z locations, followed by the resistance value that's been recorded. So it's a really simple file format. If you've never looked inside a Res2D file, it's dead simple. It's all text. And once you understand the layout of it, it's pretty easy to work with as well. But if we then scroll to the bottom of that file, what you would normally find is the last few lines of data are then followed by a series of zeros. And each one of those zeros is a kind of placeholder for additional types of information. And it could be topography. It could be that you have regions within your model that you know what the resistivity is from previous ground tests. It might be, as we're going to do now, information about the marine environment that we were working in, or it might be adding in real world coordinates so that when you come to export the data, it's georeferenced. So each one of these zeros is a placeholder. And so what we're going to do is replace a couple of those zeros with the necessary information. And so in this particular example, I just grabbed a random marine resistivity data set off my computer. In this example, the first bit we've got is information on the topography. So it has a header just to say topography is in a separate list below. We then say how many data points we have for the topography and whether the horizontal distance that we're going to give the software, whether the distance along the profile that we give the software is a horizontal distance, like absolute distance, or whether it's the distance along the terrain. And normally for resistivity surveys, it's the distance along the terrain because you are giving an elevation for each of the takeouts. And obviously the takeouts are fixed distance apart, but they're draped over the topography. So normally it would be the flag 2 rather than a horizontal distance. So then beneath that, you just list however many topographic reference points you have, and you put in the distance along the line and then the elevation. So what we've got in here is just as simple as it gets. We've got the depth of water at the start of the profile, and we have the depth of water at the end of the profile. So the first line says 0 meters. We've got a depth of 6 meters. So at 0 along the profile, the data starts at -6. Then at 500 meters along the profile, the depth is 0.5 meter. So really simple, but you could have a much more detailed profile, perhaps from a sonar or just a simple pinger for more of the electrode locations. So you can plug those in and give yourself a more complete topographic model. And obviously what the software is most interested in is then the depth of water above. How far can the current go upwards? Then the next section is a couple of zeros down, and that's where we're adding in the information about that water column. And so the first thing that we put in is the resistivity value of the water column, so the hashed area in this model. And from the measurements taken, it was approximately 4 ohm meters across the site. So 4 ohm meters for the water column, and we then also tell it whether that is relevant to the entire model or whether that's relevant to a particular part of the model. So we're saying, yeah, from 0 to 500 meters, the water column is 4 ohm meters. If you were crossing a river, for example, then your topography is going to be maybe relatively flat on either side on the floodplain. Then you change the topography in the center, and then you say there's water in that section, and that the resistivity of that water is this. So it allows you to have just predefined sections rather than the entire length of the profile with these values assigned to it. So that's setting it up. That's how we would set up the file ready for inversion. We would then load it into Res2D. It would read that information in along with the data. And then when you run the inversion, it will take that into account. But we said that one of the things that's really important for us to do when we come to the end of the process is to assess, did we really get as deep as the software thinks we did? So some software packages will automatically give you a depth of investigation estimate, a DOI. So I'm thinking here like Workbench from Aarhus Software. If you run an inversion in that, they fade the color out at the bottom of the model to show where the reliability is reduced. So that gives you an indication automatically of this DOI, depth of investigation. In Res2D, we have to actually manually do the assessment and then look at it for ourselves to work out how deep we were able to penetrate. When we run the inversion, the software is always assuming that the current is flowing to the theoretical maximum. And so for an ERT survey, that's normally about 1/5 of the spread length. So if you've got a 100-meter long spread, maximum depth theoretically is 20 meters. But if we're losing current into the overlying water, then that could be significantly reduced. And so this process is very important for us to understand. So the way that it works in Res2D is that Res2D will run extra inversions. So it will run the inversion, the normal inversion, where it takes a starting model and then changes that starting model gradually until it gets a survey result, theoretical survey result that looks very, very similar to the raw data that we've given it. What it does in the DOI test is it does two more inversions. It does one with a very low resistivity starting model and one with a very high resistivity starting model. And it then utilizes a strange quirk of inversion, which is that if you have reliable data, then your starting model is dragged towards what should be the real resistivity value for that particular part of the subsurface. If you have a lack of data or a lack of reliable data in one part of your model, then what happens is that as the inversions go on and on and on, they gradually return back to the starting model. They go back to the resistivity value that was at the start. So let's say, for example, your starting model is automatically assessed by the software as being the average apparent resistivity from your data set. If you run the inversion and you've got poor quality areas, then the model in that area will be back at the approximate average apparent resistivity. So what the software is going to do is it's going to take these two models, one with a high starting model, that's the one in red, and one with a low starting model, that's the one in blue, and it will run the inversions. It will then compare the results from both of them, and it will compare each cell in the model to see how the final resistivity value compares from the high res model and the low res starting model. Now, if you've got good quality data, good reliable data, then both models should produce approximately the same resistivity value in the final model. If you've got poor quality data, then as we said, as the inversion continues, it gradually moves back towards those starting values. And so the two models that would be produced would diverge. And so the values that you end up with are going to be separate. So the software does a statistical analysis and then presents us with the result. Let's look at this kind of with a real world data set. So at the top here, this is a final model. This is an inverted model showing the distribution of resistivity theoretically on this particular site. Then what we've got on the left-hand side is the low resistivity starting model And what we've got on the right-hand side is the result of using a high resistivity starting model. And the software makes a really deep model for this because it wants to make sure that it gets to a point where it has basically gone back to those starting values. So this is probably 3 or 4 times deeper than the real model. And what you see is that right at the bottom, 3 or 4 times deeper, where we wouldn't expect to get any reliable data, the high starting model is indeed high resistivity, and the low starting model has low resistivity. But near the surface, it's very compressed, but near the surface, in the stuff that we're interested in, what we see is that the models are very similar, and very similar to the distribution that we have in the kind of final result. So that would suggest that, hey, these are probably pretty good. And so the software will combine that and produce you a DOI plot, which looks like this. So this is the result of that statistical analysis, taking those 2 models and comparing them. And a value of 0 on this scale that runs from 0 to 1 is a perfect fit. The 2 values are the same from both of those starting models. A value of 1, which is the sort of reds and purples, that's no fit. That is a really poor correlation between the 2, and therefore suggests that the model is entirely unreliable in that area. Loke, who's the guy who was behind the development of Res2D, in his workshop manual, he suggests that a value of 0.1 is a really good cutoff to use, as kind of anything below 0.1 is reliable, anything above is probably unreliable. So in this particular color scale that runs from 0 down here to 1 up here, 0.1 is around about where it starts, the blue starts to lighten up. So we could say that in this instance, this is probably the limit of reliability. And if I was to superimpose on there the theoretical maximum depth of penetration of that particular array, that would have been around the 45-meter mark. And what we can see is that actually all of that data that was collected is within the reliable zone of measurement. So we'd be quite happy that what we're being presented with is based on good data. So I'll just take a little look at that in Res2D itself, just to kind of show how it works. So I bring Res2D up here. If I'm in, this is what Res2D comes in as. This is what it looks like on screen when you first start the software. If you go to the Inversion menu, you have this option called Calculate Region of Investigation Index. It's basically another name for a DOI, a depth of investigation. So if you click on that, the default parameters work pretty well for this. What it does by default is it uses a starting model that for the low version that is 1/10 of the average apparent resistivity in your data set. And then the high resistivity starting model uses a value which is 10 times the average apparent resistivity in your raw data. So those are going to be the 2 that it starts from and tries to run the inversion on. And then when you press OK, you'll see it go through the inversion process, just like it does when you're doing a normal inversion. And when it's completed that, what we end up with will be, in the working folder will be our raw DAT file. That's the raw data, the pseudo section. We've got an inversion file in here, which is one that we've actually processed the data with. Then we end up with these DOI1 and DOI2 inversion files. So they are the final result of the inversion for the low and high resistivity, and a text file that basically is just a script telling the software what the names of these are and where it can find them. So to analyze it, you would go into the display menu. And normally you would say model display. Oh, I haven't loaded a file in. You would open the inversion result. You would say model display. You would pick the iteration you want to look at. And we've got our pseudo section from the field, our final model, and what the pseudo section would look like if the real world had had this distribution of resistivity beneath it. And we can see that the maximum depth of the maximum theoretical depth in this instance is about 35 meters. So if I then go back and say file, read DOI files and read pair of inversion files, it will then look for that script, that text file. So you just open that up. And then we just say model display, display region of investigation. And then it shows us one of the inversions at the top, and then it shows us this DOI analysis at the bottom. And what we said was that a value of around about 0.1 is the kind of cutoff for when stuff becomes unreliable. Anything above that, we don't trust. So we can see here in the color scale, 0.1 is down here in the blues. So again, if we were to say that this is approximately the point at which it becomes less reliable, we can see that that's somewhere beyond 50 meters depth. So for our 35-meter deep model, hey, we're absolutely fine. We're up here somewhere. We're in the good stuff. So that's how we do the analysis. And as I say, it's much more important to do this kind of assessment when you've done a marine survey than a land-based one. Okay, to a couple of minutes just to finish off, I'll show a case study of a resistivity survey in water. This is one that we've used a few times in different presentations, but quite often in the webinars, it's a sort of cut down version of this. So this is a more extended analysis of project in Stockholm itself. Stockholm is built on a series of islands, and they have a plan to extend the underground railway network between a few of the islands. So they're proposing a new tunnel route, and that's going to have to cross some open water to get from island to island. The geology is pretty well known on the islands themselves. It's pretty easy to map it there, but across the water, it's less well known. But the one thing they do know is that there are a series of fracture zones, fault lines, and weaknesses in the bedrock, which otherwise is relatively strong. So they know approximately where these lie, but they don't know what impact that's had on the bedrock itself. And what we know about resistivity is that if we have good solid bedrock, we tend to have higher resistivity values, because once the bedrock starts to fracture and weaken, you get more water into it, which obviously lowers the resistivity. So this survey was actually undertaken by an engineering consultancy called OF, a Swedish company, and it was undertaken on behalf of the Stockholm Council, City Council. So the idea was collect the geophysics data that could be correlated with the sort of point-by-point geotechnical work that had been done, and produce a more complete picture of the geology that could then inform the planning of not only the route, but also whether there would be areas that would need reinforcement, because the natural bedrock, if it's strong, will actually hold itself up. GPR kind of ruled out the fact, was ruled out by the fact that this is a marine survey in salty water. So this part of Stockholm, one side of Stockholm, you have fresh water coming from the land, the other side you have the sea, and this is definitely in the salty end of the of Stockholm. So TEM and magnetic data, well, magnetic probably wouldn't have given them the answers that they were after, and TEM, although it would have mapped some of the geology, was ruled out by the fact that we're in the middle of a busy city, and there's lots of cables and pipes that are actually laid on the bed of the sea at that point, which would just cause far too much interference. Seismic would have been a great option to use, but unfortunately there were gas pockets in the sediments, and so that causes big problems in terms of the data collection and analysis. So they settled on the fact that they would use resistivity, because we know it works well in marine environment, gives us nice continuous 2D data. It's not a point-by-point measurement. It's perfectly fine with these small gas pockets in the sediments, and it isn't really that sensitive to the existing infrastructure that is on the seabed. They used a Terameter LS, 12-channel system, collected 5 parallel profiles across the water where the tunnel would be going beneath, using a single cable, a 64 takeout single cable with 7 meter spacing. And this was laid on the seabed to be able to get the best data quality, best penetration possible. To improve the penetration, they used a pole-dipole method. So that's where we have 3 of our electrodes, which is 1 of the current and the 2 potential electrodes actually were on the spread. And then the final current electrode is at some distance away, somewhere else in Stockholm. And the rules of thumb for pole-dipole survey are that that remote electrode needs to be quite a long distance away. So they had to put it 3.5 kilometers from the survey site. That means a wire running 3.5 kilometers through Stockholm. Not particularly easy, but they managed it. And they've got a pretty dense data set. They've got 3,256 data points per profile. They use Res2D to do the processing, so they'll have gone through the steps that we just looked at. And they used sonar that was actually mounted on the bottom of the survey vessel that they were using to be able to map the topography of the seabed along each of the lines. And they had one of our resistivity logging instruments to be able to measure the resistivity of the water column. Now, if you're in a relatively freshwater environment, measuring the resistivity is pretty simple because it doesn't really change that much from top to bottom. In saline environments, you find that as you get deeper, the denser, more saline water tends to be at the bottom. And so they've managed to measure a profile of how the resistivity changes with depth using our logging tool. A few photos from site. Most of the survey lines were actually possible to do from the quay side and then just using the boat to extend the end of the cable out across and then dropping it down. So as you can see from the photo at the bottom center, that's the dead end of the cable, and it's got an eye on it that was connected to a concrete mooring block, and that's dropped in to keep the cable in place. And as you see from the top right picture of the guy holding the cable, you can see that the takeouts are much bigger on these full marine cables that they were using. So much, much bigger than the ones you have on your regular cables. So here's the data that came out of it, of these profiles. So these are plotted as what we call a fence diagram. That's plotting the 2D data in their relative positions in 3D space. And you can see that there's kind of a relatively similar trend through those profiles from one side to another. If we actually look at 2 in detail, what we need to imagine is that the white area is the water column. And so then where the colors start, that's basically the topography of the seabed. And the interpretation was relatively straightforward. The very low resistivity values are associated with the sediment that has a high water content, and that water is saline, so it has very low resistivity associated with it. Then as the resistivity starts to increase, you're moving into the weathered top layer of the bedrock, so again has a very high water content. And then gradually as the resistivity increases, we're looking at better and better quality bedrock, i.e. better and better for tunneling through. This was a pilot study to see how well it worked. So they also had a pretty dense series of tests undertaken with a penetrometer, so they could push through the sediment and see where the top of the bedrock lay. And so each of these black dots is where the penetrometer stopped, where they interpreted that as being the top of bedrock. And you can see that there's a pretty good correlation between where there's a jump up in resistivity and where that penetrometer detected the top of the bedrock. So a pretty successful outing all in all. So with that, I will draw this webinar to a close and say thank you very much for attending. If there are any questions that you've thought of during the session, please feel free to put them either into the chat box or the Q&A. I'm happy to hang around for a few more minutes and answer those. If, as always happens to me, I think of the question about half an hour after the event has finished, you are more than welcome to send me an email at jimmy.adcock@guidelinegeo.com, or alternatively find me on LinkedIn and send me a message through there. Always happy to take questions.